Hi everyone, we are very happy to have Yifan here to present his work today. Yifan is a postdoc researcher at the Rio Lab, Stanford University, working with Professor Shuran Xiong. Prior to joining Stanford, he was an applied scientist on the Vulcan team at Amazon Robotics. He obtained his PhD and MS degrees from the Robotics Institute at CMU, advised by Professor Matthew. He obtained BOE from the Department of Automation at Tsinghua University. He had also spent time at Toyota Research Institute and MIT. I'll now pass the floor to Yifan.
Thank you. I assume that was Tim Yuan who introduced me. Thank you very much. Um,
Also on screen.
Oh, great. Nice. So it's my great pleasure to share some of my work with you. And I actually recently changed this slide by quite a lot. If there's any part that is unclear or you want you have some high-level question or a low-level question, feel free to interrupt me and ask questions. Okay, you can just speak up. Okay, so today I will talk about how can we make manipulation robust in the real world. Okay, so I would like to start with a review of the robotics capability nowadays, because we have seen so many new demos coming out like almost weekly. So where are we? How close are we to solving robotics? In terms of locomotion, we have seen these amazing humanoid demos coming out this year, and these are like not even Boston Dynamics style, very expensive, high quality robots. These are robots that you can buy for like a reasonable price, and they can already demonstrate a lot of impressive mobility capability. Um, on the other hand, in terms of manipulation, these are two demos coming out very freshly within the past week. One from Sunday and one from Physical Intelligence, and they are demonstrating some what I would say very impressive robotic manipulation skills. But if I'm going to show this video to my mom, she might still ask me why the robot is acting pretty dumb. I would say nowadays the robots have pretty much superhuman capability in terms of locomotion already. But in terms of manipulation, well, there is still a quite large gap between human level capability. So in other words, it seems that for robots, manipulation is a lot harder than locomotion. Now, why is that? If we look into the difficulties of manipulation closely, there are two challenges. Okay, one is the fact that the manipulation is involving a lot of making and breaking contacts. It's contact rich, and the problem with contact is that a small change in position of force could cause a drastic failure. It might cause a wrong contact mode. Another challenge is the fact that there are so many sources of uncertainties in the real world. So the small changes that we don't want are actually pretty abundant in reality. Okay, those uncertainties exist in like every aspect of the robotic system, including sensing, modeling, actuation, or sometimes even we could have disturbance forces. So on the right, we have some examples. On the top, this robot is just trying to install a light bulb, but there's a tiny slot that the bulb need to go in. The robot's position has some uncertainty, and the robot missed the slot, so that it cannot finish the insertion. Below here, this robot is trying to use this blade-like hand to flip up this item, but due to some position error, it does not. It didn't successfully insert the blade below the item. Instead, it punched around the front of the item. Although the motion looks very close visually, the result is very different. The item cannot be successfully flipped. Okay, so it appears that we really need to make the robot manipulation robust to the uncertainties in order to make manipulation reliable in the real world. So how can we get robustness? Nowadays, if I ask like some people working on robotics, the same question, like how can we make robots more robust? Oftentimes people will just say, okay, you just need to collect enough data. So I would say that's kind of true, but also not very useful because I don't think you can expect to collect sufficient data for every single task our robot need to do, because in our world, there is a vast variety of manipulation problems. Okay, you can pour in a lot of effort to make a few use cases, to make a few applications work well, but in the long term, there is just so many problems that our robot need to learn. Simply scaling data might be a very inefficient way. So speaking of efficiency, there are many good questions we can ask about how can we make robot learning more efficient? How can we enable a quick acquiring of new skills when our robot is facing a new problem? Like, does the data contain sufficient information to describe the behavior, describe the intended behavior, or is the data quality good enough in some difficult, challenging manipulation problems? The data you collected it might be very challenging to collect good quality data. And how can you debug a policy if it is not perfect? Because that's a well-known black box problem of learned policies. Because if something goes wrong, it's really hard to understand why it is wrong, and it can be challenging to correct the wrong behavior. Okay, so facing all these problems, in my work, I'm trying to grant the robot a robustness using perspective from two very complementary views. Okay, first, I look into how does manipulation work. This is basically looking into the mechanics behind robotic manipulation. And this includes to look into failure modes of robots and metrics to evaluate, quantify the robustness of a manipulation system and to perform robust control. On the other hand, I also look into how can we get manipulation that works. Okay, this is to learn robust behavior directly from human demonstrations. And on that note, I will talk about how can we incorporate useful sensing modalities, how can we collect data more efficiently, and how can we improve a pre-trained policy using human correction data. And these two perspectives actually help each other. The principles of manipulation provide guidelines about how can we design a more efficient learning system, whereas the learning from demonstration pipeline improve the generalization of model-based method. Okay, so let's start from the first one. How does manipulation work? Actually, it's a bit hard to answer that question, but the reverse question is much easier to analyze. How does manipulation fail? If we look into the instantaneous failure cases of manipulation and try to avoid them, then we basically obtain a robust manipulation policy, right? So, it turns out there are two types of instantaneous failure in robotic manipulation. The one is crashing. This basically means the robot is applying a ton of force into the environment. Like in the top video, the robot has some error in the motion direction when it is trying to slide this item up, and it creates huge internal force and breaks the fingertip. The second failure case is unexpected contact mode. So basically, maybe you are expecting some certain contact mode, like in this case, the finger is supposed to be sticking, but it slide unexpectedly. Then the item drop, and that marks the moment of task failure. Okay, and my talk in this section will be centered around these two types of failures. And since I will talk about a bunch of modeling, so I'm going to list the assumption I use. So the modeling use rigid body assumption and assume everything is quasi-static, so the robot is not moving super fast, and I use Coulomb friction model. Those are assumptions that limit the generalizability of the model, but they also enable very robust methods. So in practice, I found it much easier to use simple methods to come out with robust method, just come out with robust controller, and use the robustness of the controller to handle the inaccuracy of the model. So that's the general philosophy. Okay, so the first type of manipulation failure is crashing. It basically means the system has huge internal forces. So what caused the huge internal force? How can we analyze it? It turns out it basically means the kinematic constraints in the system has conflicts. Okay, that's a useful way to look at the problems. And there are two sources of kinematic constraints in a manipulation system. a part of them are from the environment, which basically are from the context. Okay, so you cannot have penetration at context, and if you have a sticking contact, then the cutting point also cannot slide. So they introduce instantaneous constraint on the system velocity, represented by the contact Jacobian J here. On the other hand, the robot control also impose constraints into the system. Okay, especially when your robot is pretty rigid, then your control command is essentially acting like a velocity constraint. Okay. And this tool forms a linear system on the system velocity at any point of time. Okay, and sometimes these two constraints are not compatible with each other, which means the linear system becomes ill-conditioned and there's no solution. That marks the moment of crashing. Okay. So how can we avoid it? Well, a natural way to make the two group of constraint compatible is to remove some of them, right? The system cannot take a lot of different constraints. So, but you cannot remove constraint from the environment because you can only control the robot. So let's just remove some control constraints. Okay? And that basically means the robot need to behave softly in some directions. Okay, it need to not enforce a certain constraint on the velocity. And this can be done by compliance control, especially like variable stiffness control or hybrid force velocity control. Some people also call it hybrid force position control. But these are basic methods to let the robot give up some control in certain directions. And we found that you can actually quantify how far away a system is towards being ill-conditioned using a modified condition number of this linear system. I call this crashing index because it's basically tell us how far away the system is towards crashing some items. And once we have a metric to evaluate the crashing index, we can actually find a control, find a compliance control to optimize this metric. Okay. So this type of problem is called hybrid servoing. It basically computes a velocity control that has the correct dimensionality to avoid the kinematic ill conditioning. It also computes the directions to do velocity control so as to optimize the crashing index. So even under uncertainties or disturbances, you are also very unlikely to fall into kinematic ill conditioning. And it also computes the right magnitude of the velocity control command to achieve whatever desired velocity you want on the robot or on the item. And the method can be very reliable. Here are some examples we performed. For example, on the left, this big block is the actual model that the controller knows. Here, the longer item is also the size of the item we use in the control, but the actual item size is quite different. But the robot is still able to perform those delicate manipulation behavior reliably. Okay, so looks like we can avoid kinematic ill conditioning, but that's not enough. Remember, the second failure case is unexpected contact mode. Actually, if we just use hybrid servoing, in this particular case, when you have a robot hand touching a block on the top, one specific action could cause one of the four conditions. They are all possible. There is this ambiguity that you cannot distinguish between the two, between the four. This is a fundamental limitation of rigid body modeling. Okay, so we still need a way to reliably select the desired contact mode out of many. And the key here is a distinguishable representation. Okay, so we need a way to mathematically separate different contact mode. Okay, and I found a very useful representation, which is the polyhedral convex cones in the robot wrench space. So okay, this might sound a little bit abstract, but you basically look at what are the forces the robot need to exert. Okay, so on the right, this is the space of robot wrench space. Okay, and for this particular two-dimensional case, the wrench space is three-dimensional, so we can visualize it. And if you look at forces in this dimension, then every single contact mode the system could have corresponds to a cone in this space. Okay, so you can geometrically understand how different contact modes are related to each other and how can you what kind of action you need to take to pick a certain mode. Okay, so I designed an algorithm to robustly select a contact mode using force control. So it basically first, it also utilize hybrid servo internally to come out with a compliance profile and some velocity control command, which eliminate a bunch of invisible contact modes. And then it compute the best force to select the desired cone for your contact mode while staying away from all others. Okay. And here are some examples of how this algorithm works. So first, it can reliably execute all the feasible contact modes. And you can also sequence them together to achieve a pretty delicate manipulation task, like flip up, rotating this item on its corners. It's actually very difficult to do even for human. Okay, a quick summary of what I have talked about so far. There are mainly two types of instantaneous manipulation failures, like the kinematic air conditioning and unexpected contact mode. And you can avoid them by select the correct control in your system. Specifically, you can choose a suitable compliance profile to avoid kinematic air conditioning. And you can choose a certain force, don't need to be super accurate, a rough force to avoid the unexpected contact mode changes. Okay, so that's part one. Let's move on to part two. So now we have some understanding of how manipulation robustness works. How can we learn robust behavior directly from demonstrations? Because in a lot of use cases, we cannot afford to do a lot of detailed modeling. Right? So there is a lot of existing work doing this, right? Try to learn a visual model policies directly from demonstration. However, most of them, like almost 95% of them, they are pure visual position policies. Okay, they takes in vision and position and output a position. But that is not a good idea for manipulation because manipulation is all about the process of making and breaking contact. And to describe this behavior or capture that behavior precisely, you need force and you need compliance. So to fill the gap, we augment a traditional, a standard imitation learning paradigm, basically just a different policy. We augment it with force input and compliance output. Okay, so now the policy output not only the reference position, the reference force, but also a compliance profile, which can be executed by any standard compliance controller. This is how we give compliance to manipulation policies. The key challenge here is like how can you compute the compliance parameters? Because these are not something you can directly measure. You can only measure position and force. And unfortunately, estimating compliance parameters from force and position is a underdetermined problem. Okay, we just don't have enough constraints to find a certain solution. And just to simplify the problem, we consider quasi-static motions. So we can describe compliance mostly by a stiffness matrix. Okay, so damping and inertia, those terms, they don't play an important role at low speed. So how can we get around this difficulty? So our solution is to instead of computing the accurate compliance profile, we chose to compute a useful compliance profile using our principles of manipulation robustness. And our solution turns out to be very simple. We just need to be compliant in the direction of your current force feedback. So we look at the data we collected from a demonstration. At every single time step, we set the compliant control direction to be aligned with the current force feedback if the force is big enough. And for all the other directions in your action space, we just use high stiffness. Okay, and this particular choice have a bunch of advantages. Okay, first, it provides force disturbance. It provides disturbance rejection ability in all directions. This is because the robot is either in high stiffness or it is in low stiffness, but it is maintaining some contact forces. So the external force has to be greater than the contact force to break the contact or cause any motion at all. And second, we can prove that this choice of compliance profile can guarantee the avoidance of kinematic ill conditioning under mild assumptions. And also, this enables us to use a very compact and intuitive action space, which includes reference pose, which is where the robot should be, represented by the light yellow dot, and a virtual target pose, which is where the robot compliance controller trying to go to, okay, and a number for stiffness. All of this can be computed easily from the force position data offline. When the virtual target is different from the reference pose, their difference actually indicates the desired direction of force or the direction of low stiffness. So we can use it to recover the full stiffness matrix and the reference forces. And when there's no contact, the 2 points basically coincide. So the policy behaves the same as the vanilla diffusion policy. Okay, so considering time, I won't talk about too much about experiments, but basically our method is both robust to disturbance and also safe. Okay, so we can learn compliance behavior, but in this work, we actually rely on a pretty complicated data collection system. Okay, so I built this kinesthetic teaching system that requires a person to hold the robot, and the robot need to have force torque sensors to measure forces. Okay, and those commercial force torque sensors can be pretty bulky and expensive, and they can be quite fragile. They are a limitation of extending this work to a lot more manipulation tasks, especially in a wild task. Like if I want to deploy this in somebody else's home, I have to bring the robot with me, which is pretty inconvenient. So to this end, we incorporate a very compact force sensor called CoinFT into the handheld data collection device, UMI. The benefit of this device is that it's so small that and cheap that we can afford to put 2 of them on the same device. Okay, so there is one sensor behind each finger. Okay, now with this kind of device, we don't need any robot to collect data, and we can measure all the forces that the human can feel when operating this handheld gripper. Okay. And this enables us to collect data very easily in all kinds of environments while have pretty good force sensoring. And here are a few example tasks for that we can train to use the force sensoring capability from UMI-FT. And we can reuse the ACP policy framework. So the policy can predict the reference target and the virtual target. And we also extend the policy to incorporate depth information and the 12-dimensional force information from both CoinFT. We also extend the policy to handle finger opening and closing motion. Okay, so far we have been talking about learning from demonstrations. One problem of those systems is that at initial deployment, it's pretty hard to achieve a high accuracy or high success rate. This is a general problem for imitation learning, especially for challenging tasks. There's no clear path towards reaching 100% besides just collect data extensively. So if we have a pre-trained policy and we try to make it work well on a specific task, what can we do? Usually, this will require lots of task-specific data. For example, in Gemini robotics, although their model is being pre-trained on a quite big data set, but for some challenging tasks like cable routing and assembly, they still need to collect anywhere between 2,000 to 5,000 additional demo per task. That can be quite extensive and could make generalizability pretty hard. And we have a interesting observation. So basically, for those pre-trained BC policies, even when they fail in a pretty gentle way. They're often just off by a few centimeters or even less at some critical part. Okay, and it's very easy for human to identify those failures and correct them. So can we learn from human corrections directly? So to this end, we present a work called compliant residual dagger, which can very effectively improve the success rate of challenging configuration manipulation problems. And we tested on 4 tasks, and we can improve the original policy's performance to close to 100%, and using only 50 to 100 episodes of human corrections. So how do we do that? So the method is called compliance residual dagger. Dagger is not a new thing. It's basically the paradigm of improve a pre-trained BC policy with online corrections repeatedly. Okay, it's pretty well studied in the field of autonomous driving. However, there's still no principled guidelines about how to do it for configuration manipulation. So in this work, we analyze the problem and provide contributions in 2 aspects. First is how can we effectively collect human correction data? And second, how can we use the data to update the policy efficiently? So in terms of collecting correction data, existing methods for manipulation are either observe and recollect, which can be quite tedious and hard to scale, or is being done by teleoperation and human interruption. So basically, when the human observes a failure or some about to happen failure, they take over control from the robot. Okay, and this moment of taking over and the later releasing control authority introduce discontinuity into the data. Okay, so the data quality can be less good. Okay? You can have lots of small jumps in the data collected by teleoperation. Another problem with this teleoperation style of data collection is that when you take over, you have no idea what the robot was originally trying to do. Okay, so your motion might deviate largely from what the original distribution is. So this is making the correction behavior pretty big and difficult to learn. So to deal with these 2 problems, we developed a compliant intervention interface. So instead of taking over from the robot, we let the robot policy run continuously nonstop. And when we want to interrupt, we just directly apply force to the robot handle. Okay, okay. So this way, we can the data we collected is very accurate because you can directly see in what direction you need to apply force. And the data are very smooth and gentle because it's very easy for human to apply force gently. To support this type of compliant intervention interface, we built a compliance control system using 2 force sensors. One for closing the loop for compliance control, the other just to record the net contact forces. This will be the input to the policy. And the control forms a virtual spring around the base policy output. This basically means you can feel how far away you are deviating from the base policy from the magnitude of resistance force. Okay, so if you want, you can do your correction while still stay pretty close to the original policy distribution. And we can show that our method indeed collect data with higher quality than the data collected from taking over. And the takeover data often contains lots of noise, so the learned policy also often has this random behavior, random noisy motion. And once we have the data, we tried many different ways to use it to improve the pre-trained policy. And the method that works the best for us actually is a residual policy. Okay, so instead of fine-tune or retrain, we train an additional residual policy just to learn the correction behavior. And there's a good thing about this approach, which is that since our collection data always contain force feedback, so no matter what kind of base policy it is, the residual policy can always be force aware. Okay, and the residual policy's prediction of delta pulses and the target forces can be again sent to any standard compliance controller. Okay, and from experiment, we show that training a residual actually can learn more efficiently than retrain and fine-tune. Retrain does improve the policy, but it's much less sensitive to the correction data than residual policy. For fine-tune, it can very easily go unstable, even with some regularization. Okay, so far we have been talking about a few ways to improve impedance learning, but we have been dealing with simple hands. Things are a bit different for dexter hands because for dexter hand, we oftentimes don't even have good data collection at all. Existing data collection methods often have very large errors for those dexter robot hands, whether you're doing teleoperation or trying to learn the motion from a human video, or if you use a data glove. This is because of the large embodiment gap between the robot hand and the human hand. Okay, so it's generally a very challenging problem to map the human motion into a robot hand's motion. So to this end, we propose a system to collect human dexter hand motion more efficiently. Okay, so this video demonstrates that our system can learn pretty precise and context-rich and also long horizon dexter's hand manipulation skills in this real-world kitchen environment. And we obtain these dexter skills by imitation learning, where we train our policy using data collected directly from human demonstrations wearing a exoskeleton. Okay. This is the DexUmi project, where the device enables us to do demonstration with direct haptic feedback, because you are doing the manipulation with your hand, not teleoperation, so you can feel the force. And the motion is being precisely recorded using dual encoders and also tactile sensor and vision. So whatever sensor modality that the real hand has, we incorporate that on the actual skeleton. Okay, so how do we make this work? We still need to close the embodiment gap and mirror gap, right? To close the embodiment gap, we made the design decision to duplicate the kinematics of the real hand on the exoskeleton. Okay? So we ensure that the exoskeleton's fingertip has the exact same trajectory as the robot hand. Okay? So and it basically has the same joints location, same joint limits, same link length, and the same pose of the fingertip. But after we've built our first version of a hand that has all those good capability, we found a big problem. Okay, so these hands are too close. These exoskeletons are too close to human hand, and we cannot wear them. Okay, they compete for space with the human hand. Okay, so there's a big collision, especially around the thumb, because the thumb has so many digraph. So we have to do a design optimization. Okay, we're putting our requirement on the precision, accurate tracking of the fingertip, as well as wearability requirements. And the result is a modified design where we essentially move back the location of the thumb joint without changing the trajectory of the fingertip. Okay, so after this design optimization, we have a system that we can wear where it will generate data that is compatible with the robot. So we essentially find the intersection of human range of motion and robot range of motion, and DexUmi only give you the data around their intersection. So the data you collected can be directly replayed on the robot. And on the visual gap, we also has a pipeline to make the robot, make the human hand look like the robot hand. We basically run SAM to segment out the exoskeleton and the human hand, and we inpaint the masks using images from the actual robot hand. And the result is the video demos that looks very similar to what can be collected by teleoperation, except that the quality of the demo are much better. Okay, and we tested this method on 2 different hands, the inspired hand and the X hand, across 5 tasks and several applications. A few important lessons we learned is that first, it's very critical to use relative action in your hand control, especially the finger controls. Then we can have behaviors like sticking contacts. Second, tactile is not always useful. When it is not very noisy and like for example, on X hand, their first sensor is okay, not perfect, but okay. Then having tactile actually improve success rate in some critical moment, like here when we try to grasp the thought. Um, um, Having tactile is critical because at this close distance, the camera cannot see anything. Okay, so tactile is like the only way you can tell whether you have successfully finished the grasp. But when the tactile is very noisy, it actually makes the policy perform worse. Okay, so to sum up, today we'll talk about we'll talk about a couple of different work, and they basically covers um, many different part of the whole robotic stack, right? Like we start from mechanical principles, and move to like sensing modalities, and all the way to data collection and the policy structure, and how can we reach proficiency after policy is trained. Okay, so this is also my general research interest, like how can we inject robustness in whatever way that is needed to the whole robotic system. Okay, and I will quickly talk about some future work ideas. I want to build a agile deployment paradigm. Okay, so what does that mean? One problem I noticed when I was working on those manipulation problem is that um, a seemingly simple task can have many variations and many different failure cases. For example, in this belt assembly, uh, although the final motion is basically always following a single sequence of contacts, right? It try to route the belt on the first pulley, then go for the second pulley, then rotate. So that seems to be a pretty easy process, pretty simple process. Not easy, but simple to describe. But in reality, we have gradually discovered so many different weird failure cases. Like sometimes the belt can get stuck on the base of the first pulley, and the belt cannot touch the white pulley anymore. Sometimes the robot goes too low and the belt get stuck on nearby structures. Okay. And even when the first pulley was successful, when it is trying to route the belt on the second pulley, the belt might go too high or too low and miss the slot. Or another failure case is you see there is a button around the center of the pulley. Then either side of the belt might get stuck there. Okay, so there are just so many different failure modes that we couldn't anticipate at the beginning. And it's in practice, it's very expensive and slow to discover and cover all those failure cases. But if you want to have a truly robust manipulation policy, you do need to have good coverage. Okay, so I think we can leverage simulation and the model-based method to achieve a quick coverage. I think a very interesting pipeline in my mind is like once you have a new problem, you can first perform a real to sim and build a rough digital twin of it. There is a ton of ongoing work in the graphics community that is trying to make this part faster and reliable. And once you have this model in the simulator, you can apply randomization to the scene in whatever way you want. Okay, then you basically generate a ton of problem variations in the simulation. Okay, and since you are in a simulation, you have perfect modeling information, perfect feedback, so you can potentially compute robust solutions using model-based motion planning. Then you basically end up with a data set that has a very good coverage of different context sequences, different variations for your particular task. Then finally, there could be many different ways to utilize that data set. You can train BC directly potentially, or you can try to co-train with some real world data. There is also a lot of ongoing work in combining simulation data and real world data. And the goal here is to quickly establish common sense and basic robustness for a given new task, so that you can later use it to reach proficiency using some kind of dagger or some kind of reward RL. So that's a paradigm that I'm really excited in. And there's some related prior work on once you have those contact ratio variations in simulation, how can you actually find a solution? So I think a very promising direction is sampling-based motion planning in a simulator. Okay, so we try to combine a sampling-based planning method, basically RT, with stability margins that we derive from the principles of robust manipulation. Okay, so those margins are basically metrics that evaluate how robust a certain action is towards disturbance forces. And the change we made is only to the extension step in RT. So if you're not familiar with RTs, you're basically starting from the starting point, which you treat as a root node on a tree, and then you iteratively sample random states in the system's state space. Then you find the closest point on the tree to the newly sampled point, and you try to grow the tree with feasible actions towards the newly sampled state. Okay, and we only change this growing part. Basically, it's called the steering problem, where we extend one branch for every single feasible contact mode at this point, and then we just check the robustness of every single branch using our stability margin. Then we trim off any branch that is not stable. This way, we end up with a tree that is always robust, always reliable, and can be executed very reliably using our compliance control method. Okay, so here are some examples of motion that we plan and executed in the real world. We can find pretty long sequences motions in the matter of like for 2D problem in the matter of like 10 seconds, 30 seconds. For 3D problems, usually 1 minute to 5 minutes. So I think there is a great potential in generalizing this algorithm to more general 3D manipulation problems. Okay, so coming back to our agile deployment paradigm, once we're able to quickly generate a diverse data set, and we can use it to bootstrap online learning, the true goal is to make it easy for everyone, not only us like robotic scientists or engineers, everyone to deploy robotic manipulation much easily on their own household problem. Okay, and finally, we will be able to tackle the vast diversity of manipulation tasks by basically enabling everyone to safely and quickly deploy a robot policy and improve it to obtain a proficient manipulation policy. Okay, I think that's all of the works I want to talk about, and I'm very happy to discuss with you if you have any questions.
Can I ask one question on 48 page?
Okay, 48.
Yeah, it's about Texumi. So
Here. This one?
the next page, I guess.
Okay.
You can see that actually the Texumi can handle intersection of like the human capabilities and robot capabilities, but actually that does not fully leveraging like the robot hardware capabilities. And
Right.
also the human actually can do more like also one of the motivation for using human demonstration is actually we want to learn more like let's say diverse and also intuitive like the demonstration from human, right? So so if you only can handle Texumi can only handle the intersection of them, I don't feel like they are actually fully leveraging the embodiment properties. How can you fill those kind of gaps, or do you have any like the ideas about like for example how can we leverage the full functionality of each embodiment?
Exactly. So that's a very good question. So Taxonomy indeed can only handle, it can only achieve the dexterity that is kind of shared by human and the robot. And this is especially a big problem if the robot hand looks very different from the human hand. Like if we are going to build a taxonomy for a larger hand, and if your hand is small, then you pretty much cannot move a lot. Okay, I think this face a challenge for hand design. Okay, the fundamental problem is not that taxonomy can only be here. The fundamental problem here is why the robot capability only intersect with a human in a small region. Okay, I think there is a general trend in the industry that's going to build robot hand that are more capable and look closer in form factor to human hand. So there's the trend. The industry trend is to like we are going to have robot hand where the two circle overlap a lot more. So there will be more opportunity for taxonomy. And to that end, a very interesting question is, can you design the exoskeleton and the robot hand together, like have a co-design mechanism to optimize both the motion range of the robot and also wearability. I think that will be the true that would be a very exciting opportunity to enable more dexterous hand demonstration capability.
Thank you for your answer.
Thanks for the question.
Hi. Thanks for the great talk. I have a question on the CR dagger.
Sure.
It looks like the normal way of providing correction is disjoint, while this compliant way is like more smooth. Could you explain more on like what exactly makes it more smooth? Is it because like human is not overriding action? I just want to like understand more how this makes it like more smooth compared with the normal human correction.
Right. Yeah, that's a very good question. So this is also something we didn't notice when we started the project originally. We originally tried to reproduce some real-world RL work using like a space mouse for teleoperation. But at the moment of control authority switch, like when you decide, oh, the robot is not doing something, I need to take over. At the moment of taking over, the command that the robot received suddenly changed from the robot policy to whatever command that this teleoperation device is sending. And these two might not be continuous. Okay, there is usually a gap, a pretty noticeable gap in position and force, and especially force. If the robot is actually making some contact, is applying some force at the moment of contact authority switch, it's very hard for human to instantly apply the right amount of force to maintain the original position. So you will, let's say, if the robot is like pushing something and you take over, it's very easy to see a sudden jump or a sudden drop at the moment of contact authority switching, and you have to gradually go back. Okay, and this is the source of the discontinuity, and the same discontinuity will happen again when you release control back to the robot policy. Okay. Yeah. Does that answer your question?
Yeah. Also, another follow-up question is, so when the human is controlling the robot arm, like I wonder, like for the action that the robot records down to the data set, is it a combination of the human input and the robot input, or is it just the human input?
Yeah, that's a good question. So technically, is just the human input in the sense that it is the human correction motion, right? So when we collect data, we record not only the robot feedback, but also the original policy's output. So we can see the delta between the two.
Okay.
And the delta position between the two is what we use to train the resistor policy.
I see.
But this can be a little bit confusing because we treat the force data differently because a lot of time the base policy don't take in force at all. So the force information we recorded from this force sensor are directly fed into this resistor policy. And this resistor policy predicts the expected force in the future. And this is not a delta. This is just the pure position, pure expected force.
I see. So the human completely controls the robot, but the robot still gives an action at the same time.
Exactly.
Okay, got it.
So yeah, so I guess it's not super accurate to say that the human is completely controlling the robot. The human is basically providing a suggestion by applying some forces, but the robot policy is continuously executing nonstop. Like we never interrupt the original policy's execution. That is the fundamental reason why our data is smooth. Okay, so and for human, it's very easy for us to apply force gently. We can very easily go from a very small force and gradually increase force, and we can increase force more quickly if the motion deviation is not big enough. Like we can change as we need. but you will know how far away you are deviating from it. The robot is basically behaving like a spring centered around the base policy output. Okay, you push it away further, you will feel more resistant force. Okay, so you also this interface also gives you a intuitive control of how big the correction motion is.
I see. Got it. Yeah. Thank you so much.
No problem.
Can I ask one more question?
Yep.
In
Please.
55 slide, you mentioned about using motion planning for like the discovering agile motion, right?
Yeah.
So actually from my understanding, especially using simulation or motion planning, we are assuming that we have a precise transition model to actually search. But
Yes.
in the case of the locomotion policy or like the manipulation policy, we are based on feedback. So even though the transition model is wrong, if you can provide enough distribution of data, they can learn. That is actually our assumption in the policy learning. But in the case of motion planning, like the mismatch between actual domain and also simulation actually it has a risk of divergence. So how do you think about, especially that will be even worse in agile motion? Like, just want to know about your insight. How can you actually fill the gap?
Yes, that's a very good question. I think there are two aspects in your question. First is like those model-based methods require good modeling. How do you obtain those models? Second is these models will definitely be not accurate. There will definitely be a gap between whatever you use for modeling and whatever the actual dynamics is. How do you handle that, right? So for the first part, it's actually okay to use model-based method because we are doing this in a simulator, right? We start from real to sim. So everything at the moment of solving those model-based planning problems, we already have a simulatable system. Okay, so all the modeling information, the parameters and states can be obtained from a simulator. For the second question, yes, they won't be accurate. Actually, we on purposely randomize the thing to cover more variations. So more like I would say most of those variations are different or very different from the actual scenario. But I think the purpose of this data generation is not to obtain a perfect policy directly. I think that is very hard. Even without this randomization, the sim to real gap is already a big bottleneck. But what I'm trying to achieve in this pipeline is to establish common sense, okay, a general common sense about different variations of the problem. So that in the real deployment, if the robot faces some error, it at least has some knowledge of what that error look like and what kind of direction it can use to correct that error. Like it can be as simple as, oh, if the item is a bit too much to the left, I can just push it to the right. Okay, and then a simple motion around here is likely to generate a object motion towards the preferable direction. So those very high level general idea, they will build the foundation of the common sense, which can make it much more efficient to reach proficiency later with a Dagger or real world RL. So that's why I think this general coverage is useful. Because one big limitation of existing Dagger or RL is that if you encounter a novel failure mode, you pretty much need to recollect the same amount of data for that particular context mode. Because most of existing imitation learning paradigm, they only work for like a few context sequences, a few known context sequences. They're not good at generalizing to novel context sequences. So by providing context sequence coverage using simulation, we give them the ability to quickly adapt to like small variations in the real world, because there will be no completely new case to solve during real time, because you're only dealing with small continuous variations in the real world, which should be much easier to learn using RL or Dagger in the real world. I hope that answered your question.
Yeah, so in your answer, so it's like we actually learn common sense from the real world, and then we know how to do that in simulation as well. So you want to make the robot to learn common sense in simulation to deploy in real world.
Right,
Not the
exactly.
transition model, precise, right?
Sorry, what model?
Not transition model. So like you want to
No.
learn common sense, not transition model, right?
Right. So so we are not. I'm not talking about like building a world model or something. So I'm talking about building, providing a diverse data set, so you can use it to pre-train or post-train a policy that has some knowledge of different context sequences.
Yeah. Thank you for your answer.
Sure. Thank you.
Okay, thank you very much again. And we will see you in the one-on-one session.